Hello, everybody. Welcome to our first content video for algebra, what we're going to call this advanced algebra. In this video, I'd like to talk about some very foundational algebraic properties. Well, there's really number properties, and then it'll lead us into algebra. To some very fundamental algebra properties. So what I would like to do is start out by talking about the very basic numbers. Now these are very special numbers, and according to a book that I have, it's called The History of Mathematics. It talks about these ancient aborigines that were afraid of these numbers, or were afraid of numbers bigger than this. So they based their entire number system off of just these two numbers. And those two numbers just so happens to be 0 and 1. They are the very foundation of numbers, 0 and 1. Even computer scientists, they even base all of their programming and coding and everything based off of these two numbers. If you've ever heard of binary, binary is a number system based on 0 and 1. And any number can be used as 0 and 1, but we won't go into that. So first off, I'm going to talk about how they are foundation. Any number can be broken down to either of these numbers, any number. So let's start with the number. I'm going to draw a line here. Let's start with 0. Let's start with 8. Okay. 8 is equal to 1 plus 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 1. So 8 is equal to 8 ones. But that's not all it equals to. We can do plus 0 plus 0. And then forever, we can add as many zeros as we want. Now we'll get into why that works later. But any number can be broken down into 1 and zeros. Any number can be. Not every number can be broken down into 8s. 4 can't be broken down into 8s. 5 can't be broken down into 8s. So we can't break any number down into 8, but we can break any number down into 1 or 0. Any number that can be broken down into them. Now, there's a reason for this. And it's because these two numbers are considered identities. So, for example, I'm going to write this out as the additive. Let's capitalize that A. Additive identity Now the additive identity, the reason why that works, let's just take any number. Now here's what separates algebra from other mathematics, really. Well, not all mathematics, but what separates algebra from arithmetic. Algebra is the math of relations. And in order to relate numbers to numbers, we have to be able to include all numbers, or any number, or possibly exclude some numbers from this certain spot. So we're going to say a number A. Now, we're not quite to x's yet. We're not there yet. But for right now, we're going to talk about the number A. Now, an additive identity means that I can add this number and nothing changes about the number. So what number could I add to any number and get the same number? Well, that happens to be 0. So A plus 0 equals A. Fascinating, huh? So addition is surrounded by the number 0. And any number can be broken down into 1, any number can be broken down into zeros. There can be zeros in there, but I can add that 0 to any number and it'll still maintain its its shape. It still maintains its number. So From here, I'm going to talk about addition. So we've already included addition into what we've been talking about, but I'm hoping that we have a foundation of what addition is and what an equal sign is, and that. So I'm just kind of include those in there and build from there. But let's talk about addition first off, and let's say that I'm going to add a number to itself. A plus A. Let me go ahead and separate this. Okay, so A plus A. Well, that happens to be 2A. That means that there are 2 A's being added together. Let's do it. Let's try another one. Let's do it 3 times. A plus A equals 3A. That means there are 3 A's being added together. Now, wait, let's A plus A plus A. So, looking at it from there, let's what do you think that it would be if I just had 1A? Well, of course, it would in fact be 1A. That means that I have 1A added to nothing. I just have 1A being added, and there's nothing that is being added to, so I just have 1. So now we're starting to get into the foundation of what's called multiplication. So this is what multiplication is. It's whenever something is added however many times. So let's look for example. So I'm going to write over here as an example. Let's look at 5. And we're going to multiply it by 2. Okay. That is the same. So that's like if I plugged 5 in to this A here, if I was going to plug that in, so it'd be 5 times 2. That is just 5 plus 5. Makes sense, right? This is something you've all learned before. But it is very important that you understand how these numbers are working. So if you look at A plus A equals 2A, that's the same thing as 5 times 2 is equal to 5 plus 5. Just like 2A, 2 times A is equal to A plus A, 5 plus 5. So if I was going to do 5 times 3, so let's just go ahead and write it out. 5 times 3 is equal to 5 plus 5 plus 5 is equal to, well, 15. We have 3 5s. That adds up to 15. And then any of these numbers can be broken down into ones. So when you look up here, this is technically, let's write this in red. I'm going to write it as a note. If you look at it, I'm adding 1 8 times. So this is really 8 times 1. So 1 being added multiple times. So this is the foundation of mathematics, the very foundation of mathematics. And so these are being added, and we're starting to add some texture to it with some algebraic properties in there. So let's talk about the multiplicative identity. So we have the additive identity, meaning that if I add this number, 0 being the additive identity, if I add 0 to A, I get A. From here, let's look at what the multiplicative identity would be. So let's go here. Multiplicative. Identity. So if I was going to multiply, we'll go back to A, talk about the number A. I'm going to multiply it by a specific number, and I want to get the same number as a result. So we look up here, A plus A is equal to A. 0 being the additive identity, added to A is equal to A. So that means, what other could it be? If 0 and 1 are the very most basic numbers, they are the root of all numbers, 0 and 1. what can we do here? Well, we can multiply it by the other one. Well, 0's already been used, let's use 1. So a times 1 is equal to a. So let's try this out. Let's try what this would, if we were going to look into this, which we'll get into exponents next week. So let's just leave it there. So we're going to have multiplicative identity, a times 1 is equal to a. Here's a few examples over here on the side. We'll go back to 5. 5 times 1 is equal to 5. Yeah, so there's you an example. All right, so going from there, now we're going to talk about the different types of numbers. So we've built upon the numbers. We've talked about the identities, the very foundation of numbers. Now we're going to move on to the different types of numbers. So I'm going to write at the top numbers, because that's what we're categorizing is numbers. Now, some of you might be thinking this is very basic and you really understand it and you don't need any help with this and you can go on and do your assignment. That's fine. But if you don't understand this, it's going to be very difficult later on in the class. So if you don't understand this, please watch the video and make sure that you're learning the information. So let's go ahead and categorize these numbers. So numbers are categorized by first off, we can break any number into two different types of numbers. And those two numbers are, let me straighten that line out. Those two numbers are real, and I don't know if any of you have heard of it before. So you have a real number, and then from there, whenever you break it off into two, you're left at, let's say we take all the real numbers out. What are you left with? Well, they're called complex numbers. Complex numbers. Now, there is a real part to a complex number and there is an imaginary part. So I'm just going to write over here a plus bi, and I'm going to draw a line here saying that this is real and this is imaginary. But we're going to get into those numbers later. We're not going to deal with them right now. So let's look at the real numbers. These numbers can be broken into two numbers as well. So real numbers can be broken into, some of you are already guessing it, rational and irrational. I'm going to capitalize that. Irrational. So real numbers can be reckoned into rational numbers and irrational numbers. So real number, pretty much if you can count it or think of that like if you know the number, it is in fact a real number. Now from rational, I'm going to give you like a set of what they look like later, but I'm going to just show you how the numbers are broken up from here. Irrational kind of stops. We don't break up irrational numbers anymore because they are a group of their own. And they're very limited. There's, as interesting as it is to say, there are less imaginary numbers than there are rational numbers. I'll go ahead and say it. I'll say it. I said it. So anybody you want to challenge me? Okay, so rational. Let's look at the different types of rational numbers. Rational numbers then from here, rational numbers can be broken down into integers. From integers, so these are called subsets is what they are. So integers are subsets of rational numbers. And then from here it'll be whole numbers. We really don't deal, like whenever you get up into, if you get up into upper level math classes, they kind of just forget about whole numbers really, and you deal more with integers and natural numbers. So that leads us into the next natural or counting numbers, but I'm just going to call them natural. Natural numbers. So that's how numbers are broken down, and that's how they're categorized. Numbers can be either real or complex. Real numbers can be either rational or irrational. Now, rational numbers, from here, all integers are rational numbers, okay? And all whole numbers are integers, but not all integers are whole numbers. So that's kind of how the chain works from there. So then whenever you separate it, now I couldn't divide it because whole numbers are integers. It's not like I'm dividing from here. We're just categorizing smaller numbers, anyways. So rational numbers, then integers, and whole numbers, then natural numbers. So now from here, I'm going to show you different sets. So I'm going to start with real number. I'm going to start with rational numbers. So let's look at rational. Now keep in mind, all of these are real numbers. Rational numbers are 0, comma, it could be 1/2, it could be 3/4, it could be 5, it could be anything. So that's what rational numbers are. I can't order them because what comes after 0? Would it be 1 and 1 over 1 billion? No, well, because there's 1 over 1 trillion as well, so I can't order the rational numbers. Now, if I look at the next one, which is integers. Oh, by the way, the reason why rational numbers are called rational numbers, so we learned about ratios last year in geometry. Rational numbers are any number that can be written as a ratio, so it can be written as a fraction. Any rational number can be written as a fraction. Okay, so that's the reason why they're called rational numbers, is because ratios are fractions, or fractions are ratios. So from here, let's look at integers. Integers would be, now we're getting into some negative numbers, -3, -2, -1, 0, 1, 2, 3, ... Now we're going to go on to the next. So we just went from integers. Whole numbers. Whole numbers. This is what they look like. 0, 1, 2, 3, and so forth. So the 3 dots means that it extends in either direction. So I can go from -3 on the integers, I can go -3 to -4 in that direction. And on this one, on the other direction, I can go 3 to 4 to 5, and then just extending forever in both directions. Now, whole numbers are 0, 1, 2, 3. The negative numbers are not whole numbers, but they are integers. Now let's go on to the next one, which is natural numbers. And these are the whole numbers, but without 0. 1, 2, 3, and so forth. So the reason why they're called natural numbers is because, well, they're called natural numbers or counting numbers. The reason why they're called natural numbers is because we naturally count that way. 1, 2, 3, 4. We don't say -3, -2, -1, 0, 1, 2, 3. We naturally count 1, 2, 3, 4, and so forth. All right, so that's how the numbers are broken down. These are the numbers that we'll be dealing with mostly. Okay, let's talk about irrational numbers, because we will get into irrational numbers later on. Okay, so I'm going to separate these. Irrational numbers cannot be written as a ratio. So rational numbers are all of the real numbers that can be written as a ratio. Irrational numbers cannot be written as a ratio, meaning that they're non-terminating, and they're also not ordered. So I can't write square root of 2 and then square root of, I don't know, the next rational number. So rational numbers, so I'm going to write some famous ones. Pi is irrational. e is irrational, square root of 2 is irrational. I'm going to put parentheses around this. We'll say 1.2347 2, 1, 7, and then so forth. That is not that is in irrational numbers. It's non-terminating and it's non-repeating. So like 1/3 is an example of a rational number because 1/3, although when you put it in decimal, it's 0.333333333 forever, it is it is repeating. So that means it can be written as a rational number. Now, there are more, so I'll put a little dot. I'm not meaning that to continue, but I'm saying that there are more types of irrationals. There are more rational numbers than what I have written here. Okay, so those are our irrational numbers. So now let's talk about algebra. Algebra is, in essence, so let's go ahead and write algebra. In essence, is mathematics dealing with relationship. Now, some of you might be thinking, well, I'm in a relationship. I have a boyfriend or a girlfriend. So does that mean that there's math, that I am math because I'm in a relationship? Well, I mean, maybe there might be a relationship math based on that, but this is a relationship between numbers, so how numbers are relating to each other. And we're going to see how numbers can relate to each other no matter what. So let's look at y's and x's. So I'm going to put that in parentheses here. Y, I'll just go to say equals x, or y, we'll just say y x. Well, I will keep it proper and say xy. This is algebra. So the relationship between x, y, it could also be x, y, z if we're in 3 dimensions, so forth. But for this, we might get into 3 dimensions at the end of the book. But at the beginning of the book, we will be just dealing with 2 dimensions, which is x and y. So we've already talked about 2 properties, which was the additive property and the multiplicative property. So from there, I'm going to go into the inverse property. Because they're negative numbers, there's division. You know what I mean? Because we talked about addition, we didn't talk about subtraction. We talked about multiplication, but we didn't talk about division. Okay, so let's talk about the additive inverse. So A plus. So it's an addition, so it's an additive inverse, so adding, addition plus. And what am I going to add? All right, so now we are defining subtraction, which is the inverse. A plus negative A is equal to, you guessed it, 0. Now, if you notice, 0 is our additive identity. So A plus negative A is equal to 0. An example, I'll go ahead and write an example out. We'll say, we'll stick with 5. 5 plus negative 5 is equal to 0. Now, notice, some of you are getting ahead of me and going into the other properties, but we'll go ahead and write it out. And I just won't tell you what property I'm using. 5 plus minus 5 is the same as 5 minus 5 is equal to 0. So that's how it works. All right, so let's go on. Let's go to the multiplicative. Multiplicative inverse, so we're multiplying, so let's write our A out, and we're going to be multiplying, so there's a dot. And what are we going to be multiplying by? No, not negative A. It's going to be 1 over A. And what do you think it's going to give us? It is going to give us 1. All right, let's look at an example. Notice that I got the multiplicative identity as my answer, just the same as I did in the additive inverse. So an example of this would be, we'll just stick with 5. 5 times 1 over 5 is equal to 0. And then I'm going to write this out, 5 divided by 5, using that property that we talked about earlier, but I'm not going to mention it yet because we haven't gotten to it. All right, so 5 over 5, these are not 0. You're probably screaming at your computer screens. Okay, so 5 over 5 is equal to 1. Yeah. So there's our multiplicative inverse property. So let's go into our other algebraic properties. The first property we're going to talk about is commutative property. Commutative property. Now, commutative property is things are commutative. They can commute, they can move, they can change. Okay, so let's stick with our A's. I'm going to add a B this time. So I can rearrange this as A plus B equals B plus A. I can also arrange, so I'm going to write an example over here. Let's say that I have x plus 5 plus y, and what does that equal? That also equals, let's move that over. That also equals 5 plus x plus, I'm going to change that to y, and also equals y plus x plus 5, and so forth. So I can rearrange these things using the commutative property. So that's how the commutative property works. Now we'll go on to the associative property. Some of you are probably yelling at me because of my handwriting. Oh well. So the associative property means that two numbers can be associated with each other. So A plus B plus C is equal to A plus B plus C. So like it's funny saying that because like A plus B plus C is equal to A plus B plus C. And so that's what the associative property is. And it is very useful because now we know that I can move that parentheses around within an equation. And I'll show you how that kind of works. And so I've always thought it was funny how we learn order of operations, which is parentheses, exponents, multiplication, division, addition, and subtraction. So please excuse my dear Aunt Sally, that's order of operation. I've always thought it was interesting that we learned that before using these properties, but these properties are the reason why we have order of operation. I don't know. It blows my mind the order that we learn things sometimes. So an example of this would be, let's say, x plus 2 plus 3, and I'm going to add a y at the end of this. And I'm going to write this equal to, well, I'll just move it over. So give myself more room. Is equal to, I'll just write it first, 2 plus 3 plus x plus y. So what it's saying is that that group of numbers I can move around. And I can also move, since this is addition, I can move it around. So like, if you notice over here, it's b plus c. It's also a plus b over here. I can write it as x plus 2 plus 3 plus y. equals this, it equals the same thing. So I'm just going to put an equal sign over here. So all these equal, all of them equal each other. Okay, so the next thing we're going to talk about, and it's everybody's favorite. Let's change the color back. It's distributive property. Distributive property. So distributive property is, now we're going to put in some multiplication. A times B plus C is equal to A times B plus A times C. So if you notice, I'm going to draw down here as a note. If you notice, A was multiplied by B, and A was also multiplied by C. And we'll go ahead and do an example. Example will be, let's say, 5 times x plus 2, 5x plus 10. So what did I do? I multiplied the 5 by the x. Well, I'll go ahead and write it. 5 by x plus 5 times 2. And then that's what I got here. So these are all equal to each other. So those are our foundational algebraic properties. Now, I'm going to write out a problem, and I want you to tell me what properties I would need to solve for x. So we're going to solve for x. Let's write this out. Solve for x. This is for everybody, and there's going to be a spot that you can put in your answer in on Google Classroom. So whenever you make it to there, you can type it in there. So solve for x. We're going to do, let's say, 5 times x plus 3 is equal to, we'll say 4 plus 2 plus, let me rearrange this. 5 times x plus 3. Let me do this one as an example, and then I'll give you one of your own. That's what we'll do. Yeah, so I'm going to give you this one as an example, and then I'll give you one, and then you'll have to answer. So 5 times x plus 3 is equal to, we'll say 3 plus 3 plus 2 plus 1. Yeah. So I'm going to go ahead and write this out. So it's going to be 5 times x plus 15 is equal to, now what property did I use there? This is the distributive property. Distributive property. Now 2 plus 1, 3 plus, 2 plus 1 is 3. I'm going to go ahead and write this down below. X plus 15. I didn't use a property there, I just added. Now 3 plus 3 is obviously 6. Now, whenever you add everything inside the parentheses, you don't have to, you don't need the parentheses anymore. So I'm going to go ahead and get rid of those. Okay, so now this is when it's going to get tricky. I'm going to write this differently than you might have seen it before. 5x plus 15 minus 15 equals 6 minus 15. Now normally we would have written it underneath it and then crossed it out, right? Well, this is what I'm doing here. So the 15, I'm going to use the inverse property right there, the additive inverse property. So let's use our additive inverse property. Well, I'll go ahead and I'll write it up here. I'm also going to write these in different colors. Well, okay, let me go ahead and just solve it, and then I'll write what properties I used. Okay, so now from here, I subtracted 15 from both sides. I get 5x is equal to 6 minus 15. We're going now into the negatives. So 6 minus 15 is minus 11. Okay, so now we're going to multiply each side by 1/5. Or in other words, divide by 5. And I get x is equal to negative 11 over 5. Now, I'd rather you leave it in a fraction form than instead of writing it out as a decimal, because it's more precise. Sometimes decimals can be inexact in an estimate. Well, I don't want estimates. I want 11 over 5 as a fraction. So now let's talk about the properties that I used here. I'm going to write these in green. This was the distributive property. No, I don't want green. Let's use red. Distributive property. Distributive property. So I'm not going to write property. Right here, I just added. So, I mean, I could say additive property, but it's not really an algebraic property, so I'm going to skip that. Right here, I use the additive of additive inverse. And that's how I got from here. This was just adding them together. And then right here, used to, you would have divided by 5, but I'm showing you why you would have divided by 5. And this is the multiplicative inverse. Okay, so those are the three properties that I use to solve for x here. Now I'm going to give you one of your own. And we're going to say this is homework. Also going to separate this. And we're going to do something similar. We're going to do 3x plus 1 is equal to 3 times do 3x plus 3. 3x times plus 1. Solve for x. So I'm going to write over here. Solve for x. Tell me which property you used. Okay, I'm going to draw a little box around that because I can. Yeah. All right, so I want you to solve for x on this problem here. Whenever you solve for x, tell me the properties that you used. You don't have to write it out like I did here, like distributive. I used distributive here. I just want to know what properties you used to solve for x here. All right, that's all I have for today. Let me know if you have any questions. Thanks for watching. Thanks for your patience. And I'll see you in the next video. Thank you.